Today we're going to talk about nonlinear models. As opposed to fitting a straight line into a bunch of experimental data, a nonlinear model refers to fitting another function that is not linear onto experimental data. So we are going to first talk about defining nonlinear models. We are going to have a specific example, which is something that we all are familiar with, which is the example of transmittance related to UV visible absorption. And then we are going to demonstrate how to use SOLVER in Excel. So let's begin then by talking about the example of the UV visible absorption. Here we have a series of equations that are familiar to anyone who has been working with UV visible absorption, which is the definition of transmittance, defined as the relationship between the light that is going through a sample over the light that would go if no sample was present, and multiplied by 100 to express it as percent. We also have a relationship between transmittance and absorbance, in which the absorbance is equal to the log base 10 of the transmittance divided by 100. Now, in UV visible absorption, we normally fit a straight line, so this will be a linear model, to absorbance, in which we can plot absorbance as a function of the molar absorptivity, the path length of the cuvette that contains the sample, and C, which is the concentration of the analyte in the sample. As opposed to a linear model, we also have nonlinear models. If we use the equations above of absorbance and the equation of absorbance and transmittance, we can combine those two equations and solve for transmittance as a function of molar absorptivity, the path length, and the concentration. If we want to plot transmittance versus concentration, we will see from this expression that we have a nonlinear model in this particular case. So let's assume then that experimentally we would like to use this information to plot a series of concentrations and experimentally measure transmittances and find what the value of the molar absorptivity will be if we assume that V is equal to 1. So now let's have a look at examples of this experimental data using Excel. So I just opened up a set of data in an Excel sheet that shows concentration as a function and transmittance for each of these concentrations of the analyte. And the idea then is that if we plot transmittance versus concentration, what we will observe is a series of points that correspond to a nonlinear model. So what we would like to do is to figure out how to use this data to fit a nonlinear model to this experimental data. So the way to do that then would be to understand what the linear model might look like. So we will basically take the experimental data of concentration and the respective value of transmittance. And as we saw, it was a nonlinear model. And we will define a mathematical expression that connects the two of them, that is, transmittance as a function of concentration. And the idea would be then that if we take this overall expression and we use Excel nomenclature, we can write a formula that will represent the same transmittance as a function of concentration. So that formula then is calculated for each of the rows And then what we have to keep in mind is that we have to do this calculation, a given value of epsilon, or molar absorptivity, and B. In general, we will assume that B is equal to 1. So the value that we are assuming right now for epsilon, or EB, is given on this particular cell. So we can see then that as we basically assume a value of 10 and use the expression that is given here, we obtain different values of transmittance for each of the rows. The other component that is important for a linear model is that ideally we would like to have as close as possible the value of the transmittance of the model to the value that was experimentally observed. Clearly, as indicated by the double-headed arrow, the value for the first row is very different, 99.97, from the value that was experimentally observed. We define how close or far these are by calculating their difference in the adjacent row or column. And then we're elevating that to a square. That is so that if differences are positive or negative, by elevating them to a square, these differences disappear. And we see how good the approximation or the fit is by adding all of these residuals squared and then determining how big the addition is. If the model was perfect, then these residuals squared should be equal to 0. So what we're going to be doing here then is, in this particular type of fitting, is we're going to have what we call a decision variable. The decision variable will be that we can adjust, so that as we adjust this decision variable, the values corresponding to transmittance will change. We will also have an objective value, which in this case is we're trying to minimize. We're trying to make it as close as possible to 0. And sometimes we also have restrictions to the work that we are doing. In this particular example, for instance, we want EB to be greater than 0. In other words, a positive value. So now let's go back to Excel and see how we can adjust the decision variable to obtain different values and find out what is the best way to fit the model. In the Excel spreadsheet, what we see now is we have the original data, which are concentration and transmittance. We also have the fit data that refer to the values that result when we use the value of EV given in cell G2. And we also observe the residuals squared corresponding to the differences between, say, for cell D2, difference between the cell B2 and C2. So what we would like to do then is modify the value of EV, which is the decision variable, to minimize the value that we have here. Let's do as an example, what happens if all of a sudden I change this value to, say, 30? We can see that the values have been readjusted, and at the bottom of the screen we can see the function that we are trying to adjust here. The fit is the orange series, The experimental data is the blue series. So 30, it doesn't look good enough. We can go now to 100. Still not good enough. We can go to 500. Not good enough. 1,000. Not good enough. 10,000. We begin to see, as we do that the model, the nonlinear fit, is beginning to get closer and closer to the blue one. Say 20,000, and it's even closer and closer. So we can do this manually, but that would not be a good and efficient way of optimizing this function. So for that, we are going to use another software available in Excel called the SOLVER package. In order to do this, what we will do is that we will go to Tools, Excel Add-ins, select Solver Add-in, and after doing that, we can go back to Tools and we will see as one of the options in the drop-down menu, Solver. We open Solver and we'll get a dialog box. This dialog box allows us to set the objective, which in this particular case is the cell D212, which represents the residuals. It allows us to tell the optimization software that we would like to minimize. We select minimum. We also want to change the variable, which in this case is in cell G2, which is the value of the extinction coefficient EV. And then we're going to have a constraint. We want this number to be positive, indicated in this box here by having a value much greater than 0.0001. Once we have done those selections, we are going to select the solving method, which in this case is the GRG nonlinear. This method is really good when we have functions that are pretty smooth. So we are going to now select solve, and we will have another dialog box appearing, and we'll ask what sort of response we want. We will select, for this particular example, we want to have a new sheet that has answers. We also would like to have an outline of the reports. So we will click OK, and the net result from that is a new value for EB, or epsilon times the path length, which is in G2. And we also see in the orange markers the fit of the function defined by the column in C. So in summary then, we need to define an objective, which in this case was minimizing the residuals, defined as the objective of the cell position, minimizing the residuals. We were adjusting the values of the cell G2, which corresponded to the epsilon B values. We wanted the numbers to be positive, defined in this part of the dialog box. We selected the method GRC, which is nonlinear for smooth functions. And when we had the second dialog box, we kept the solver solution. We selected to report the answer and outline the report. And by doing that, we were able to demonstrate that we are able to fit a nonlinear model to experimental data. This is going to be extremely important in the rest of this course.